Hello everyone. Hope you're well. Hope you can hear us. I'll just wait maybe a couple of extra seconds so that everyone can join. Okay, I think we can. I think we can start now. So, hello everyone. Hope you're doing well. Thank you for joining us today for our webinar. Webinar is titled "Computer Vision: Classical Approach versus Deep Learning." Thank you for coming. I see plenty of people from different time zones. Thank you for taking the time out of the day. So I'm Vedin. I'm the Chief Business Officer at BroutonLab. I'm also happy to introduce Anna Berger. She's BroutonLab's Chief Data Scientist, and Anastasia, our computer vision researcher and engineer.
Hi all.
Yeah, BroutonLab, to maybe give a bit of a background, is a data science company. We're dedicated to helping tech startups and companies launch complex AI solutions with the help of fractional hiring and agile development. So over the years, we've been working with amazing clients. So we've been active more than 4 years now, and we've helped them launch amazing AI products. We help startups raise funds, grow in value, and eventually get acquired as well. So I would highlight that our area of expertise would be computer vision, natural language processing, development of text-to-speech models. We do it by applying deep learning techniques, machine learning techniques, as well as classical algorithms. And in the spirit of that, today so we will introduce and define two distinct approaches to computer vision in specific: the classical approach and the deep learning approach. So we will break these two down. We'll compare them with regards to different metrics, different requirements that can be added, and we will explain how they can potentially work together. So without further ado, I will allow Anna and Anastasia to take over and start first by defining everything and giving a brief overview. Please, if you have any questions at any time during the webinar, please write them in the chat. At the end, we will have a dedicated time to go over the questions, answer them one by one. And also, we can have, if someone wants to add something, we can add you to the stage as well and speak with us. So yeah, I will let Anna and Anastasia continue.
Thanks, Vedin. So today we're here to speak about computer vision, but what is it actually? I would put it like this, that computer vision is quite an interdisciplinary field, which main goal is to understand and automate tasks that human vision can do, but still this is more of a metaphor. So people always tried to replace or to replace themselves in some tasks by computer, and maybe this understanding of images, videos, is what they really want to have. And this whole area of research is called computer vision. It started like quite 50 years ago, but we will talk about this later. And I would like to maybe introduce the classical approach to computer vision. And in my part of today's presentation, I want to tell that even though the classical methods are old, they are not stale, and they are often used even now, and they can be very useful in practical applications. So the major idea of the classical approach is depicted on this pipeline, and I think that two main distinctions of deep learning approach is the path selection areas of interest and feature extraction, because in this part of the it's required from data science to engineer feature and to engineer these features and select these important areas himself or herself. And I think that that is more or less the main distinction uh, between this classical and deep learning approach. And maybe with all this popularity of deep learning, the first problems that come to mind with respect to computer vision, image classification, object detection, and so on. But I'd like to show a couple of examples of different computer vision problems that are still very um, that are still very needed by society, and in which classical algorithms are still widely applied. So first of all, it's SLAM, or simultaneous localization and mapping. The main goal of it is to construct and update their positions and the state of an agent and their surroundings, in a very with very limited resources. Usually, so you can imagine that it's widely used in robotics, in building augmented reality, in self-driving even, but we will talk about this a little bit later as well. Uh, another example could be optical flow estimation, when we want to either to track and or to predict the movement of some object. And again, in this case, classical methods are still widely applied, and can be very practical, and can serve at, and can provide you the quality at the highest level.
As I said before, for deep learning approach, we don't need a handcrafted feature. The learning algorithm encapsulates feature instruction. The main objective in deep learning approach is to train to train pipeline in the end-to-end manner. So the inputs to the neural network, we feed images with some ground truth labels, and as output we get some predictions, and the purpose of the whole pipeline is to minimize errors between these targets and our predictions. The learning algorithms themselves represents the artificial neural network, usually with convolution layers. Each layer extracts its own features from very low levels of the earlier layers of the network, like something like edges of some orientation or some blocks of pixels the same color, to the very high level features like maybe object like features from the uh, last layers of the network. Compared to the fully connected layers, the convolution layers have fewer weights that leads to less memory usage and speed up all computations, and this allows us to create more sophisticated architectures and to solve more difficult tasks. Also, another benefit of convolutions can be that if our object of interest are located in different places at the image, we can still to detect it and to recognize it, and this made convolutions exceptionally suitable for the image, for task with image that requires work with images, and for the computer vision itself. So I think that can be said that without convolution-based architectures, we doesn't reach the state of the area that we reach now. And I think there is like here we need to talk about the history of computer vision, how it started, how it's going, what's more important in the history.
Yeah, I think I should start because like classical algorithms really originated earlier. I would start with inventing first digital image scanner, because like many like algorithms, or at least the basis for them, were developed even before that time, like Fourier transforms, for example. But this is the year when the first image was actually scanned, was actually transformed into binary form, and it was possible to actually do the processing of it. Then it's really hard to select milestones in classical algorithms, because there are like so many of them and they developed quite differently. But I would select, for example, edge detection problem, for which one of the first good, quite good solutions like al- Zober filter appeared as early as in 1968, and then later developed in 80s with cannon detection, and the 90s and so on. And another important problem that still arises in many areas is object detection. And it's hard to believe that only like 20 years ago we had no idea of deep learning for this problem. And it was the time when HARLAC features were introduced, and it was like a real breakthrough at that time, because both in the terms of speed and quality of the prediction. But now we're not using them that much, given that we have these breakthroughs in deep learning, of which Anastasia will talk about.
Well, and firstly, I want to say about this event that in 2012 AlexNet won ImageNet, and it considered the breakthrough moment for convolutional neural network. Why it is? The AlexNet, it's a convolutional based architecture, and the ImageNet is the largest recognition competition that contains over a million images across 1,000 classes, and from its inceptions, it's like a benchmark for image recognition in different categories. And so from 2012, all architectures that won this competition were convolution based, following the AlexNet. Also, I would like to talk about these two events that you can see at the slide. In 2014, it was idea of generative adversarial networks introduced. So what is this? It's like the idea that two neural networks um, can be trained faster and better when they compete each other. The main idea that we have this the discriminative network that need to classify our data synthesized or its real data. And we have generator that generates the data, and its purpose to fool our discriminator, and to make it decide that the synthesized data is real. And since creations of the idea that finds its application in many spheres, like image super resolution, like convert grayscale images to the color, face enhancement, and so on. And also, I put the event that happened in 2015. It's deep face facial recognition algorithm. Its purpose to distinguish uh, to recognize and identify the current person, and it makes this great in 97% of the time. And after this event, The the coverage of news of deep learning of computer vision deep learning in the media grow by 500%. So it's like at the moment when computer vision will meet like public, and I think it's important moment also. Uh, so
So it was very interesting to hear about both approaches. Definitely, everything you mentioned about deep learning still sounds a bit newer, a bit maybe fresher, especially since you mentioned how the also the media and the papers started covering more of this area since these major breakthroughs. Still, I'd say that we should give each approach a chance and try to understand which one works better in different situations, and how to make a decision, how to use a specific word. So what are these different requirements that need to be analyzed? So I'd love to hear more about it from you. I think we'll start with accuracy. Am I correct?
Yes, you're correct. And speaking in terms of accuracy, I would advocate for using classical approach for relatively simple problems, as they still can provide a good quality. It's quite a good quality for them. Or if your scope is limited, then probably also shouldn't worry about introducing to more complicated stuff into your product. But then on the other hand, if there are data sets of high quality available for your particular problem, then it might be that classical approach would be inferior to deep learning, and it is known that it's prone to some errors, especially when there are some geometric variations like rotations, and sometimes you even don't expect rotations to be there, but they still occur because it's like real in the real data. So still, in these cases, so deep learning should be chosen over classical ones.
okay, so I continue with deep learning approach. Actually, the success of deep learning approach depends on many factors, uh, and data is really crucial to deep learning algorithms, and the quality of results strongly depends on the data set. Only when data is collected, good webbed, cleaned, and well processed, we're ready to choose architecture. And when we choose right architecture, we can expect the good results. If for different problems, when we get the data, we can expect that deep learning approach can solve problem even if deterministic algorithm doesn't exist, or it's too hard to implement, or for example it takes a lot of time or resources to be computed. In some cases, neural networks can outperform even human performance. I think all of you hear about game Go, but in computer vision we have the same famous example that in the ImageNet competition about it, as said before, the in 2015 the neural network performance were better than human performance, and classification task, and uh, the human performance for about 5% error rate, and in 2015 the neural network decision has only 3.6 error rate percent, and it still decreases over year. So we can assert that it decreases even more. But uh, but deep learning can fail in some cases when input data is very different from the data set, and we need to think about it too.
Sure, and there is like more, there is a great tendency nowadays to move all the computations to the edge devices. That's why the question of the required hardware and software, both for inference and probably even for training, is is rather important. And so I would say that with classical methods, we usually have less strict hardware requirements because these solutions are usually CPU based, and often by major companies they are very CPU optimized. For example, Intel does it, Nvidia does it. Nvidia does it actually for GPU also, but again, it's like some proprietary developments. And so it leads to easier on-device execution, especially if your device is not that powerful, which makes it also cheaper to have. And speaking of the software and maybe this process of software development, classical computer vision algorithm often allow you to start simply, maybe establish some baseline with several lines of code, especially since there are several computer vision libraries. But on the other hand, covering all special cases that occur in your data may result in a longer development process, and so the overall complexity of the code and of the solution would be higher than it could have been with deep learning.
Okay, and neural network itself, it's mostly a GPU-based solution. I mean that we can execute it on CPU, but the performance speed will be far from satisfying. I mean, I have such experience. I test the detection algorithm on both CPU and GPU from the same input video, and it's and more than an hour on CPU and about 10 minutes on GPU. So it's the difference. You can see that difference is significant. And from the software side, it's mainly more than two couple of lines, but we have a lot of frameworks that made the development pipeline easier, helping to write only meaningful lines of code, and also some frameworks aims to speed up experiment management and but on the other hand, the speed of producing experiments still relies on available resources. So, in short words, the better GPU can speed up not only the inference process but also the training.
Yes, and we were constantly also mentioning data, both for classical methods and deep learning. But on average, I would say that for classical computer vision, less data is needed, especially because training is usually not involved. Sometimes it is, but not. It's not often the case. It also sometimes allows you to start with even without like proper data collection, maybe with a couple of examples. But we should always have in mind potential problem that we can fit to particular conditions. So the usual rule that the more data we have, the better applies everywhere. I think.
Yeah. Well, we talk about data a lot, and that's because the data is essentially important aspect of both approaches. But for deep learning is crucial, and good data for computer vision means firstly wide variance. So images should include many different kinds of objects of interest, because when data doesn't not reflect the diversity of real world, we can meet the mistakes in a real life application. Secondly, the data should be good in quality, in its resolution, or at least well pre-processed. And the thirdly, the quantity of data, the number of samples required, it's depends on particular problem, but usually the more data, the better results. And the process of gathering data and processing can be time consuming. Also, sometimes the process of data labeling requires like something like industry specific knowledge, for example for medical data, or also it just can be time consuming, for example to getting masks for segmentation. um, I think no, and we also can meet the problems that we overfit to the current data set. It's when it doesn't contain the all variants of data that we came that we meet in real life.
Yes, and speaking of real life, uh, the next point to discuss is the domain expertise, and I think that in from the point of view of classical approach, it can be both advantage and disadvantage. So imagine that we do have this domain expertise. Then it will help that then this expertise will help data scientists develop good features, because as you remember, good features are engineered by data scientist himself or herself, and it makes it easier to inject this domain knowledge because we know particular places where we can do it, like in pre-processing step or in the feature engineering step. So that's good. But on the other hand, if imagine that we don't have this domain expertise, and then it would be more difficult, and in some cases maybe even impossible, to create something meaningful. And then and in this case, maybe our features will won't be optimal as they could have been, and so that also poses some problem when we don't have it. So again, so what is about deep learning in this aspect?
Generally speaking, with a good data set, when we know for sure that data is clean and we really doesn't need domain knowledge, we can choose a state-of-the-art architecture for our problem and get a good results. But as I said before, for some tasks, even labeling can require specific knowledge. And another example that I can think of some situation when our model give wrong prediction for some inputs. We expertise can help us uh, to understand, to suggest what's the reason for specific inputs, why we get wrong predictions and bad performance. But generally speaking, we can avoid this integrating domain expertise in deep learning. Let's talk about regulations thing.
Yes, and I think that this problem arises mostly when the product goes actually to the market, and I hope that mostly products do. And in this, and again, this is maybe one of the recent trends that uh, people and governments want the methods to be transparent and interpretable, because they want to understand why these or that decisions these or those decisions are made. And also people who are actually using your product sometimes can not trust enough that your product, you cannot trust enough your product. And with classical approach, it's simpler, again, because feature engineering is an obvious step. So usually it's easy to look at these features and somehow understand why the model is making these decisions. And what I personally like about classical approach is that they often have the established scope of applicability, which means that for some approaches, we can definitely say that they are to be applied here, but for these particular for these images, they are, for example, not applied. So or these videos will be for sure wrongly predicted, so we should invent some different approach to them. And knowing this beforehand sometimes saves hours of work, and sometimes this is like a good way to improve the the overall quality of the whole system.
Okay, but for deep learning, and when we talk about neural networks, we talk about the black box concept. It means that we can't interfere with the pipeline and understand why the model has made a decision. Due to this, there can be problems with using deep learning-based solution in some heavily regulated fields like healthcare, military field. Also, if datasets, like said before, didn't suggest great variance, the ready-made solution can have the same bias as, training data have, and it also can be significant obstacle to embed deep learning solution in most important spheres of our life, because people doesn't trust, doesn't understand what why it made decision following way, and this can be significant problem and obstacle.
So the conclusion, the way I understood, is that both approaches can be valuable in certain cases. So as I've seen, the positives of one approach are usually the negatives of the other, and vice versa. So the question here is it possible, is it actually desirable to kind of combine both approaches within the scope of a certain more complex project, and when does it make sense? So I'd be happy to find out about such a problem, such a solution.
Okay. As an example of the heads that can achieve the hybrid approach, we can talk about autonomous driving. And self-driving systems are extremely difficult. They combine a lot of challenges of computer vision. This system should be able to build a 3D map of the road, to recognize vehicle, pedestrians, traffic lights, uh, recognize signs, follow the rules, and so, and to be able to solve this another problem, uh, use is used as deep learning and classical approach together. And I would like to talk about uh, two examples of deep learning application to the problem. And on the slide, you can see output the output of the model that segments the road scene. This is important step of preprocessing step to speed up many algorithms that build the 3D structure of the road scenes, and as the road segmentation in such cases used to discard large image areas and impose some constraints to the objects in the scene. And also you can see the on the second image, you can see the example of detection and recognition. Neural network can be used for obstacle detection, traffic signs detection, the recognition, line lane detection, and so, and also for vehicle and pedestrian detection. And this information can be used for motion tracking that can be done with algorithm from the classical approach. And Anna will continue explain about this.
Yeah, as Anastasia has just said, so self-driving projects are mm, actually consist of many small parts. Sometimes they're not so small, but and still in some of them, classical approach still in very much of use. I can't so it's hard to say about all of this project, because many of them are quite closed, and they just don't want to share all their knowledge. But from what from what we have experience with. So tracking is using, of course, object detection models as the basis, but then the tracking is done with classical computer vision algorithm. The most like simple and popular is like Kalman filter, but there are like many extensions over it. Which and not to my mind, not the last thing in choosing classical approach here is their speed and their ability to work in the limited resource conditions. What is more, I could give an example of depth estimation. Again, it's a complicated area, but still most of it often happens that classical approach is used in this area. I know that there are some very promising works in depth estimation given stereo pictures made by deep learning, but from our experience, they are still mostly research oriented, and in real life, depth estimation is still mostly done by combination of lidar signals and classical methods, post-processing or processing them, so that to achieve best results at the potentially suitable speed. I would put it like this.
Anastasia, thank you so much for sharing this information, especially the last part about autonomous vehicles. It's interesting to think about it in this manner. And as you mentioned, like this, the speed and the performance being so important, especially in such an area where you under any circumstances you try to preserve human life as the first requirement. I hope this information will be useful for everyone who is starting or already working on a computer vision project or a startup. If you like to know more about BroutonLab in general, I'd suggest that you can register at our fractional hiring data science webinar. I'll just keep the pop up here. You and you can always click on it. I think in the bottom left corner, if I'm not correct. And so the conclusion to this whole, I would say, story is that everything, as with pretty much any kind of problem you face in daily life, everything is dependent on the particular problem, particular industry, particular data that has been collected or available in the open source. And the work of a data scientist is to understand the needs and choose the most suitable approach. So it's not just about in data science and how BroutonLab works with data scientists and clients from the US and all around the world working on AI solutions. So it's not just understanding the models, understanding the statistics or maybe mathematics beneath. It's also more about actually knowing the actual business of our clients, diving deep into the problem and suggesting development based on what's available. Of course, in an ideal situation, you have plenty of data, you have you have a clean data set, you have all the time in the world, maybe all the resources. However, in Broughton Lab knows, and our data scientists know that it's important to be able to work under limited resources, no matter what this resource is in the end. The hybrid approach has a lot of potential, and it's kind of trying to take the best of both worlds. The hybrid approach doesn't have to be maybe too explicit. It would rather say that with the sudden surge of deep learning in the various industries, plenty of people are getting into it, even as a hobby, even as a maybe side project. We would advise everyone to realize the importance of classical computer vision, dealing with images kind of in a more personal way, let's say, and before maybe going to deep learning, where it's a bit more not sure how I would put it, maybe abstract. So the conclusion was that, and I want to thank Anna and Anastasia for sharing this information. I hope it will be useful for you. I've shared the link if you want to learn about BroutonLab in general and how we work. Now, what I love to do is give you a chance to ask anything. You can do it via chat, or you can, if you want, I can just invite you to the stage to come speak with us if you're interested. Uh, in the meantime, I have while we'll possibly be waiting for some questions. In the meantime, I have shared the poll. So I would say from the poll results, it's more about either deep learning or experimenting with both. And maybe classical approach doesn't get the love it deserves, but it's actually a logical thing, I would say, especially with the hardware that we're able to use today with all the GPUs and its shortage. Especially now that everyone is looking for GPUs for various reasons. It used to be just for gaming, but now everyone is trying either to mine cryptocurrencies to use them for all different purposes. Maybe the deep learning community is now waiting for them to become more available. And so also what I wanted to maybe mention before we end is that now I've changed. So you can also check out some of the computer vision project that we worked on our website. If it looks interesting for you, maybe it will inspire your new project and give you maybe a bit of more in-depth view of how BroutonLab works and what are our favorite projects. So either way, if there are no questions, please note that we're always available via email, via our website, via LinkedIn. Feel free to contact us with any kind of questions. Maybe now it's not a good time, but we at BroutonLab are always interested in learning about innovative and groundbreaking either startups or products, especially in the AI industry. We are fans of computer vision, of natural language processing, text to speech, and we're over the years we've been actually very lucky to be able to work on something that was quite innovative, quite interesting for us. I'd like to thank you for attending. I hope it was interesting. I invite you to reach out regarding anything. If you have a computer vision project or startup that you need help with, feel free to email us. We'd love to set up a call, just learn more, maybe see it as a consultation and see how it goes from there. I wish you a great rest of the day, and we're looking forward to seeing you again soon. Thank you so much, and goodbye.
Thank you.
Goodbye.
Thank you so much. Yeah. So don't abandon classical computer vision approaches.
Don't do it, and Orana will be sad.
Yeah, I will be. Yeah.
Thank you.
Thank
Bye.
you.
Thank you. Bye.
Bye.